Hello, happy Monday. Welcome to the most intense math problem that you will ever see on a Monday. We are going to combine a lot of things we've been working on, including solving non-homogeneous equations using reduction of order and our initial value problem that you can see here. So it's been a little bit since we've done reduction of order methods. So part of this will be to review going through that again, because you can see that's our hint here. We only have y sub 1, and so we are going to need to use this method in order to find y sub 2. Now, before we do that, we're going to have to take our differential equation here, and we're going to have to get this into the standard form. So we're going to divide everything by t squared. So I'm going to get y double prime minus 1 over t y prime. All right, plus 1 over t squared y is equal to 1 over t. And this is how I know I have to use non-homogeneous methods here, because I have 1 over t here is my g of t. All right, so this is part of why we're using reduction of order and going through to find y sub 2. So we're going to use that and start with the homogeneous portion of this, and then we're going to get to the non-homogeneous portion. So let me go back black ink here, and let's say that because I know that y sub 1 is equal to t, that I know that that means that y sub 2 is equal to some function u times t. Remember, we always take u of t, just some function, and multiply it by our original y sub 1. So we are going to find the first and second derivatives of y sub 2, keeping in mind that u is a function, so we're going to have to use product rule here. Okay, so there's our first and second derivatives, and then we take this with reduction of order, and we plug everything in order to figure out, our goal is to figure out what u as a function is. Okay, so we are going to plug this back in. Here now I have my standard form up here. And it really doesn't matter for this, actually, what we plug it into. So we can plug it into the original. And I kind of prefer that just over having to, work with fractions over here. So I'm going to plug it in to the original. Oh, and actually, that you saw I wrote equals t there really quick. So we are going to do this to find the homogeneous portion of our solution. So we are going to go ahead and use equals 0 for that to find the homogeneous differential equation solution here. All right, and so and that's why too, it's probably good to go back to the original and just set it equal to 0 there. Okay, so remember, we take this form, we go through and we multiply and we simplify everything we can, and then we see what we're left with. And with reduction of order methods, sometimes we had to do an additional substitution to simplify. So for this, if I multiply everything out, and I see I get a little simplifying here. We get a negative TU that cancels with a positive TU. And then it also looks like I have some U prime terms here that I can combine. And I'm going to do this in the order where I keep my derivatives kind of in that descending order. So I'm going to keep t cubed U double prime out front. And then it looks like I have a positive t squared U prime. And then this is equal to 0. So I do, in fact, have to do a little substitution here because I see that when I simplified it down, I still have a first and a second derivative. So the way that we went about that before, if you remember, we introduced a new function that we called w, and we say w is equal to u prime. So that way, if I take the derivative of w, then it's equal to u double prime. And we do this so that way we have a first order differential equation because those first order differential equations are separable. So we have t cubed, and this will be w prime plus t squared w. And this will be separable for me. So that way I can just solve that differential equation. So I'm going to get on one side t cubed dw dt. On the other side, a negative t squared w. And then all my t's on one side, all my w's on the other gives me 1 over w dw equals a negative 1 over t dt. And integrating both, I'll keep that negative on the outside. And that's going to give me that the natural log of w is equal to the negative natural log of t plus c. This is a little laggy over on this side. Okay. So I want to exponentiate both sides. We're going to do a base of e to cancel with that natural log. But remember this property we learned that if I have a negative natural log, I'm going to return that as an exponent on t so that I actually can cancel that e to the natural log. Okay, so this is going to return here so that e to the natural log will cancel out. All right, so on my left-hand side, I'm left with w. On my right-hand side, moving that negative over leaves me with a t to the negative 1 plus c, and that's, so let me do just an intermediate step here. I get e to the natural log of t to the negative 1 plus c. And if I use my operations with exponents here, I would separate that into e to the natural log of t to the negative 1 times e to the c. So if you remember that e to the c coefficient there, because it's multiplicative, just becomes one big c value. So w equals c times t to the negative 1, since that e to the natural log will cancel. All right, so we have what w equals, and we're going to undo our substitution here. W is u prime. So essentially, if I would like to go back to my original u value here, I would say that it is u prime that equals c over t. And then I would find that u then would have to be equal to c natural log t. All right, so I have u, and remember u is just a part of my y sub 2 solution. So y sub 2 is u times t, and I now know that u is equal to c natural log t. So y2 equals u times t, and plugging in, that means y2 equals t times the natural log of t. Remember, all those c's kind of come out into the general solution anyway. And so for the homogeneous portion of my solution, y sub h, I get c1 times y1, which is t, plus c2 times y2, which is t natural log of t. All right, so let me just notate here that t is coming from my given y1, and t natural log t is what we just determined for y2. All right, we are part of the way there, and I will not solve the initial value problem with you, but I will get us through this new part here, which is solving the non-homogeneous portion of this, because we only have part of our answer. We need our full y of t, which is y sub h plus y sub p. So we have found y sub h, and now we need y sub p. Well, y sub p, according to what we learned in 3.9, is equal to v1 y1 plus v2 y2. All right. And we went through the whole process and we learned that I've got this matrix equation that tells me that v1 prime, v2 prime is equal to 1 over the Wronskian times my matrix over here consisting of a negative y2 g of t element and a y1 g of t element. So we can figure out the Wronskian, and we also know y1 and y2, and we also know g of t, right? G of t comes from when we got this into the standard form. So it really doesn't matter to get it into standard form until this very step where we're solving the non-homogeneous portion, but we're going to remember that g of t is equal to 1 over t. So I'm going to first find the Wronskian. W of t. Remember, we make our matrix with y1 and y2 in the first row. So we've got our y1 is t, our y2 is t natural log t, and then their derivatives. So y1 prime is 1, and I get to do a little product rule with y2 prime here. So I'm going to get the natural log of t plus 1. And then finding the Wronskian there, we are going to get t natural log t plus t when I distribute minus t natural log t, since that's just multiplied by 1 there. So we get a little simplification here, but our Wronskian is not equal to 0, and that is really the key. So my t natural log t's cancel out. That leaves me with a Wronskian determinant of just t. All right, so again, this is not equal to 0. So we know that this does form a fundamental set of solutions, which is a nice byproduct of doing this method because we solved for that y2. So it's probably good that we're going through this whole thing and verifying that that does form a fundamental set. So plugging it all in now to what we had up here, we are going to say that our matrix equation v1 prime, v2 prime is equal to 1 over t times negative y2, which is negative t natural log t, times our function g of t, which is that 1 over t. So we're going to use that to simplify a little bit. And then our second element here is y1, which is t, times g of t again, 1 over t. So that'll simplify nicely. I don't know why I did a bracket. All right. So keeping in mind, we're going to simplify each of those elements, but then they also get multiplied by that 1 over t that I have on the outside of my matrix. So that is going to give me these two elements, negative 1 over t, natural log t, and 1 over t. All right. Now, the rest of this is integrating and getting V1 and V2 into this form for the particular solution here. So I'm going to leave this video at that before it gets much longer and leave the answers so that you can look over and see how you did with the rest of that. So good luck. I hope you have a wonderful Monday.